So, in continuation to this first reaction, that is nucleophilic substitution reaction, we have seen that in this reaction, an alkyl halide, the halogen is being replaced by a Y minus, which is a nucleophile, and you will get a new compound, Y containing compound, and NaX will be out. So, this is a nucleophilic substitution reaction. In the last class, we have seen this mechanism of this reaction, under what condition the Y is able to substitute, and the Y should be the stronger base. Huge number of examples we have seen, and the mechanism is with reference to the kinetics. It is classified into SN1, SN2, and the SNI also. We have seen how this the implications of this the carbocation stabilization and all that also we have seen. We take the, in continuation to this, relative reactivity of different halogen compounds towards the reaction with reference to this nucleophilic substitution reaction. Even if nothing is mentioned also, generally it is in terms of or with reference to the SN1 type of reaction, whether it is mentioned or not, it is SN1 type, because the compounds like to pass through the carbocation. So, therefore, with reference to the SN1 reaction, even if nothing is mentioned or default, we have to take it as a SN1 reaction. So, the first order is a benzyl halides undergo faster reaction over the allyl halides, over the alkyl, over the vinyl, and lastly aryl type. Let us take an example for this each category. Benzyl means benzene next. So, let us take benzyl chloride. This is more reactive than the allyl means, an example, ethylene attached to CH2Cl. Then alkyl, let us take one example, ethyl chloride will take. Then ethylene containing a double bond is called vinyl chloride. Then an aromatic compound, that is a benzene directly with the chlorine. So, this is the generalized order in which, so we divide this order into the two parts. The first is why this benzyl and allyl are more reactive. This is taken as a standard. Let us take with reference to this standard ethyl chloride, why these are more faster, or in the second level we will take why these two are less reactive. So, let us first discuss why these two are more reactive. Means both these compounds remove the, if a Cl minus is removed or ionized, what you will get is called a benzyl carbocation, which has got a resonance stabilization by means of this minus M group, that is this the electron pair of the benzene is given, and a charge comes into the ortho and then para and then ortho. Like this, the charge is delocalized, and thereby the benzyl carbocation has 1 plus 3 resonance structures, and this is stabilized one. Through this, when once this comes, the second step is an ionic, so therefore it will be a fast reaction. Similarly, even the benzyl chloride also, allyl chloride also, if you this minus of Cl minus, if you remove the Cl minus, you will get a CH2 plus, which has got a resonance stability. This double bond will come here, and you will get carbocation this side, and so this and that will be goes on showing the resonance. So, therefore, resonance stabilized. However, now within these two, why this is means you have to claim that it has got 1 plus 3 resonance structures, whereas this has got only 1 plus 1. So, in the resonance, as the more the number of structures are there, more stabilization. So, once this ion is formed, the product formation will become easy. Therefore, it is also studied that among these 5 types, the first one, almost with hot water, the reaction takes place. The condition required to get the benzyl alcohol, just hot water is enough to undergo hydrolysis reaction. Whereas here, you take water and boiling water. Boiling water means beyond the 70 degrees, the reaction taking place. Here, you need a dilute NaOH and then boil it. Otherwise, reaction will not take place. In the vinyl chloride, you need a concentrated NaOH and then boil it. Here, in the last case, you need 3 conditions. One is concentrated base should be there, and high temperature should be there. High temperature, that is around 350 degrees centigrade. This is not that difficulty, but high pressure. The high pressure means around 150 atmospheric pressure. This is normal pressure will be 1. So this is 150 means very, very high pressure. Normally in the laboratory, you cannot have any flask to withhold that high pressure. Only industrially it is possible. Under these 3 conditions, one, if we preparing a phenol from this one, is called a Dow process. It is called the commercial processes actually, the plural. So the actual method will be in between these 3. The parameters can be changed and you can have a suitable the method actually. So the chlorobenzene will give the phenol in this case. So why these 2 are more reactive means the answer is coming that from this stabilization of the intermediate. Now why these 2 are less stable? See, the condition required is only at elevated temperatures reaction taking place in the case of vinyl and the aryl. Why means the reason one is the molecule itself stabilizing. It is not the intermediate, as we have seen. Intermediate or the final product stabilizes, reaction takes place fastly. Starting material stabilizes, reaction come down. So this is in this case the vinyl chloride as well as chlorobenzene, both the starting compound is stabilizing. Okay, that is starting material. Starting compound stabilizes. This is the first reason. There are 3 reasons we are claiming. The first one is starting compound is stabilized. The second reason is in the resonance structure, let us write the resonance structure of vinyl chloride. In the vinyl chloride, the chlorine becomes into double bonded, but this is polarized to here. You will get this side minus is formed, the chlorine gets a plus charge. And finally, what you observe is between the carbon and chlorine, if single bond is there, someone can cut and replace. But if it becomes double bond, it is difficult to replace. So therefore, the C and X acquires a partial double bond nature. So therefore, it is difficult to cut and replace with a new group, that is either the OH minus and so on. This group is becoming a double bond. That means 1.5 bond, 1 bond, 2 bonds. Average, if you take 1.5 bond or stronger bond, it is becoming. Therefore, it is difficult. Another one also. What is the group you are going to replace means chlorine is being replaced by the OH minus, a negative group we are implementing. See, the minus is attacking. In the saturated system, the chlorine pulls, so this carbon acquires a positive nature. So on the positive, Y minus attacking is justified. But here this carbon is unsaturated. Unsaturated means a sp2 carbon, electron rich carbon. So electron rich carbon will not allow to attack the Y minus, isn't it? Rich carbon will not allow a nucleophile. So we know that electron rich carbons allows electrophiles, that is what the alkenes and benzene undergo electrophilic attacks, and however the reaction is a electrophilic addition or electrophilic substitution. But first of all, electrophiles will attack. Now here you are trying with a nucleophile, that is conceptually a reverse reaction you are trying. So nucleophile attacking on the electron rich carbons is difficult. And when you compare the aryl versus vinyl, resonance structures are again 1 plus 1 here. Here 1 plus 3 resonance structure. So More the resonance structures, more stabilization. Here one and double, 1.5 bond. Here one single bond, thrice it will become the double bond, that is 3/4 time double bond character is. And the benzene is also highly rich than even the double bond. So as the electron rich is more, nucleophile attacking is difficult. So all these three cases are there here with a more vigorous. So therefore the reactivity is becoming down. So ultimately the order what we say is, first comes benzyl, then allyl, then alkyl, then vinyl and aryl. The question can be, any two compounds can be given and asked which is easily undergo hydrolysis, or can also be like this, a common compound can be chosen, like for example, so this is a halogen is there, let us say there is one halogen, there is another halogen, there is another halogen. Out of these three halogens, and simultaneously if I add some sodium hydroxide and boil it, which halogen first replaced? That means this middle one is a next to double. This is called allylic type, this is vinylic, this is alkyl. So as per this order, first allyl get, then alkyl, then vinyl, isn't it? That is the order. Like that, compounds can be, different compounds can be chosen and asked question, or in a one compound you can have this type of the three different halogens are there, they are numbered with X1, X2, X3, which halogen is more reactive also can be asked. Then you have to classify that halogen into double bond attached, so therefore it is vinyl. Double bond next to carbon, therefore it is allyl. Okay, this is not influenced normal one, alkyl. So allyl number one, alkyl, then vinyl, that is the order chose. So therefore one can easily justify that if it is 1, 2, 3. So the second one comes first, then comes the third, then comes the one. So that is the order. In fact, it is nothing but the alkyl, allyl followed by alkyl followed by the vinyl type. The three are given in this suitable example. So another example is, within the alkyl we have a tertiary alkyl halides. Tertiary alkyl halides are more reactive than the secondary, than the primary. So that is for example, a tertiary butyl chloride, right, is more reactive than a secondary butyl chloride, is more reactive than a N-butyl chloride. These are the three different varieties, 3 degree 1, 2 degree 1, 1 degree 1. Why it is so means 3 degree gives a carbocation which has got 3 inductive effects and 9 hyperconjugation stabilization. Here only 2 inductive effects and 3 plus 2, 5 hyperconjugations. Here 1 inductive effect and 2 hyperconjugations. So therefore, as the stability of the carbocation is more, that's what it is with reference to the SN1. If somebody really asks with reference to SN2 what is the order, one has to reversely, you have to say this, N-butyl chloride undergoes faster reaction towards SN2. In the SN2 carbocation will not come, stabilization cannot be taken into granted. So therefore, with reference to SN1 or overall, nothing is said, you can take it as a SN1 and then adding 3 degree, 2 degree, 1 degree is the order. The question can be a commonized example, like for example, this is a 2-chlorobutane. You can have a chlorine here, okay, chlorine here and a chlorine here. There are a chlorine 1, chlorine 2, chlorine 3. Out of these 3 chlorines, first which chlorine undergoes hydrolysis means first the chlorine 1 undergoes first hydrolysis because its carbocation is 3 degree. The chlorine attached to 2 degree comes, second chlorine undergoes, then next, then last the chlorine third halogen. So like this the degree oriented is the classification here. So 3 degree alkyl halides undergo faster than the 2 degree than the 1 degree. If all belongs to the same category, that is all are primary, let us say, then you can have another order here. That is if all are methyl halides, then you can take methyl iodide is the more reactive than methyl bromide, than methyl chloride, than methyl fluoride. The order can be justified that if CF bond, if you consider, it's a very strong and stable bond. remember that the fluorine carbon is very strong and stable, cannot be hydrolyzed fastly. So therefore, methyl iodide. So iodine has got ambiguity. Incoming also it comes first, outgoing also first. So now we are taking as the outgoing property, which goes out fastly means iodide goes fastly. So alkyl iodides undergo faster hydrolysis. However, in the case of aromatic, it is different. That is, aromatic fluoride compounds are more reactive. That is, fluorobenzene undergoes faster hydrolysis over the chlorobenzene, over the bromobenzene, over the iodobenzene. That means in the previous case we said iodide is faster hydrolysis. Now I am saying the iodide is weaker. If all are single bonds, the fluorine makes a strong bond, therefore less. Here the fluorine can be single bond or can show the resonance also. In the resonance, fluorine carbon will become double bond. In the case of iodine, iodine also shows plasm effect and shows a double bond character. Now, which of these halogen shows better plasm means the iodine is a less electronegative. So therefore, more plasm effect. More plasm effect means more double bond character. More the double bond character. More double bond means difficulty to hydrolyze. So you can have single or double means this always have a double nature. This will have a mostly single one because the fluorine is more electronegative. More electronegative shows more minus I but less plasm effect. Less plasm means double bond will not be formed in this case. So therefore, the fluoro compounds undergoes faster hydrolysis. Even with ice water, it is said some references. With ice water, fluorobenzene can undergo the nucleophilic substitution reaction. That's why if all are the aliphatic case, methyl iodide is fast, but in aromatic case, phenyl iodide is going to the last. You can also have one more order. If all are aromatic, the aromatic containing withdrawing groups like 3 nitro groups are there, then the hydrolysis will be very easy, it seems. Why this makes means this nitro shows a resonance. You can write the nitro separately like this, a double bond O and a O. If this polarizes, the double bond of the benzene polarizes, you get a positive charge on the carbon where chlorine is attached. In such a case, what happens? A nucleophile like OH minus will feel easy to attack on the carbon and replace the C. Even this nitro also creates a positive on the originally on the ortho to this one, then goes to para, then goes to the ortho. Like that, all these nitro groups will make a positive charge at least one time on the carbon where chlorine is attached. So therefore, they all are pulling. So overall benzene ring is deactivated, that is reaction, electrons will be removed. So nucleophile attacking will become easy. Electrophilic attack difficult, but they are all withdrawing. So therefore, nucleophile attacking on the carbon will become easy. So trinitrochlorobenzene comes first, then a dinitro, 2 nitros let us take, ortho para dinitro, okay. Then a mononitro. In that mononitro, better take a paranitro over a metanitro. Actually, how do you justify this? Meta is lagging over the para means. With reference to inductive effect, this should be the stronger because it is closer to the carbon. But where the positive charge it is creating means on the ortho to this nitro, on the para to the nitro, on the ortho. That means the carbon where chlorine is attached is influenced. Whereas this nitro creates a positive charge here, ortho to nitro and para to. This none of them, these 3 positive charges are on the carbon where chlorine is attached. Therefore, this nitro can only show minus I effect, overall ring is deactivated, but down to the chlorine carbon is not influenced. So therefore, the minus I is working in this case, but minus M is not working. So therefore, here the minus M is working, minus I is a little far away, but minus M is working in this case because suitability is there. That's called position factor, in fact, we can say. So, this meta will be lagging. However, over that, an ordinary nitro, that is without nitro, a chlorobenzene, over that you can also say a group donating like OCH3 type of groups are there, then they are activating, and this, that is donating plus some effect will make minus and minus and minus. Already benzene is minus, and if OCH3 creates a minus, attacking of a nucleophile or a OH minus, attacking on this carbon will become highly difficult. Therefore, hydrolyzing or nucleophilic substitution on such a donating groups, whenever it is containing, the reaction will become much more tough. So, withdrawing with more number and less number, out of this the positional, that is either at ortho or para, is more reactive than at meta, than ordinary chlorobenzene, than a electron donating group like methyl or OCH3 and so on. So, donating groups will have a much more difficulty. So, these 5 different varieties of the examples can be taken, and more complicated examples, in fact, blended type of the another concept, one versus second also can be mixed and can be, questions can be framed. So, let us go to the another second characteristic reaction. This is the elimination reaction. In fact, these two are the more important reactions in the halogen compound, that is, one is nucleophilic substitution, the other one is elimination. The other reactions are not that important. If you cover even in the syllabus also, the more emphasis is there on these two questions. Elimination is simply represented like an ethyl chloride when treated with the alcoholic KOH and heated for some time. So, you will get a one from one side one hydrogen, the other side Cl is removed, that is minus of HCl is taken away. This HCl reacts with KOH, forms KCl and water, but the main compound will be the CH2 double bond CH2, and ethylene is formed and the KCl and water is formed as a byproduct. This is alkene is formed, and ethylene is formed from the ethyl chloride, giving this type of alkenes and losing a HCl. It's, you can say technically dehydrohalogenation is taking place, but this is the one of the characteristic reaction of the alkyl halides. However, you can take as a second characteristic reaction of the halogen. So, with reference to the mechanism of the reaction, here also the reaction is classified into the 3 types it can be. One is elimination, 2 elimination, 1 that is bimolecular, unimolecular. The third variety will be the E1CB, that is a elimination unimolecular through conjugate base, elimination unimolecular through so there are 3 types of the reactions are there: elimination bimolecular, elimination unimolecular, elimination unimolecular through conjugate base. What is this reactions? Let us see. First, let us take in the E2 reaction, how the reaction proceeds. So, first let us see the details of this E2 elimination. It is a relatively little simple mechanism. So, we are going to remove the one H and one Cl from the compound. Therefore, let us give importance for these 2 groups more. So, when I treat it with alcohol dissolved KOH and then heated for some time. So, the OH minus is taking the first Cl minus. This OH minus will come and grab this hydrogen, however. So, it is coming, if it comes from the side of the Cl minus, however, it will have some opposition, the negative repulsion. So, leaving except from this side, it can come from the other side and can grab this H plus. These 2 electrons will go to this bond Why only this bond? Means it is pulling. So therefore on this carbon there is a positive. So therefore electrons will be traveling this side, and these two electrons will be withdrawn by the Cl. Take that the OH coming and taking the hydrogen as a small bit called A bit, and this is B bit, that is withdrawal of the electron toward this bond. Withdrawal of these electrons is taken as a C, let us say. All this A bit, B bit and C simultaneously taking place. The whole reaction will be only one step. It is step 1, that's all. There is no step 2 here, that is single step reactions it is, okay. All will takes place in one single step it is. Simultaneously taking place, a double bond is formed. The 4 hydrogens retain in the compound, but a double bond is acquired between the 2 carbons. So alkene is formed, and this OH and H forms water as a one byproduct. The Cl left over will go with K and then forms KCl. So this all takes place in one step reaction it is. So OH will come and take away the H plus, 2 electrons will be coming and making double bond, and these 2 electrons will go. All takes place simultaneously. So therefore the rate of the reaction will be directly proportional to the alkyl halide concentration as well as the concentration of the OH minus. So therefore it is called bimolecular, that is 2 molecules concentration is influencing the rate of the reaction, therefore it is called bimolecular elimination. So that is, so any one of the concentration like OH concentration I increase, reaction will become more because more number of collisions will be there. More alkyl halide concentration, then also reaction becomes fast. That's why it is called a bimolecular elimination. Now let us take have a E1, that is unimolecular elimination, right. So in this elimination, we see the compound what I am taking is again the HCl is a must to show the reaction. But the other groups instead of hydrogens, let us take all big alkyl groups if you have. Then essentially the halogen containing carbon is a 3 degree one. And where the hydrogen is there also, if it is 3 degree, the discussion will be much more easy now. So whenever the KOH, when you add and boil it, the same alcoholic KOH only I am taking. The OH minus, as I said, if it want to come from the side of the Cl, there will be a negative repulsion will be there. If it comes from the other side, the alkyl groups will be so big enough and they are almost covering the area where hydrogen. Unfortunately, the size of the hydrogen in the picture, alkyl and the hydrogen size is shown same. But literally speaking, the hydrogen will be so small when compared with this hydrogen, the alkyl. Alkyl is minimum 1 carbon with the 3 hydrogens, means 1 carbon means 6 electrons, 6 protons, 6 neutrons. Whereas hydrogen means 1 electron, 1 proton. It's very small when compared with the alkyl. So that's why the OH cannot find the actual hydrogen size wise when all these alkyl groups are occupying the entire area. The finding the OH, this proton will be difficult. Therefore, this attacking the OH on the H plus will be slightly difficult. This we are claiming as a steric hindrance. That means a problem due to the non-availability of the space. So this we are claiming as due to the steric hindrance, the OH cannot approach the proton. So therefore what happens means the reaction should not take place, but the reaction taking place very nicely. So therefore we have to propose another mechanism here. That means now what happens, instead of OH attacking, first Cl will go out. This is called step 1. In the step 1, minus of Cl minus. If Cl goes out, then this carbon will become a carbocation. So the carbocation will have a symmetry, trigonal planarity, right? So when the moment Cl goes out, the carbon will become into sp2 hybridized carbon. The trigonal planarity symmetry is formed. So this reaction will become slightly better, that is favorable factor is there. What is that means? the angle between the two alkyls is now right now 109 degrees. This is becoming a 120 degrees. So, the sterically the problem is becoming a favorable side. So, therefore, the reaction has got some. As the size of the alkyl is big and big, the ion formation will become easy. This is called steric hindrance relieving the problem. So, therefore, we have a better this one. Another one is all these alkyls will have a plus I effect, and then the Cl will have a outgoing property, more outgoing property. So, more the alkyl groups push it, the Cl will pull it and then go out. So, that is another factor. The third one is 3 degree carbocation is stabilized. 3 degree carbocation has got the stabilization. This is the ultimate the stabilization factor. So, therefore, in the case of 1 degree, even if Cl goes out, you get only 1 degree, that is not much stabilized. There is no push and there is no steric hindrance relieving and all that in the primary. So, primarily this 3 degree, that is tertiary alkyl halides, will have all these multiple benefits here. So, finally, first Cl will go, a carbocation is formed, the alkyl groups and the hydrogen will be there. Now, the OH minus attacking has got some favorable other factors also. What is that? Now, the 3-dimensionally both the sides alkyl groups are hindering here. The moment Cl goes out, it will become a trigonal planar. So, the OH will approach this proton from this side of the plane or from the back side of the plane. So, either way it can come and grab this hydrogen. So, with reference to this paper type of the plane, it is not a 3-dimensional, it has become a 2-dimensional. So, from the side of this plane or from the other side, the OH come and beautifully will grab this hydrogen, and the 2 electrons of this bond will be given to the bond, and then you will get an alkene formation with the 2 alkyl that side and the 2 alkyl this side, right. Now, here we have a small argumentation slightly deviated from this mechanism, that is, when OH is coming by the side of this carbocation plane, it may be attached or allowed to attack on this carbon. Why not? This carbocation will attract, and if the OH attacks on this, then what happens? You will get a nucleophilic substitution reaction, that is ethyl alcohol is formed. That is what we discussed in the first characteristic reaction, that is nucleophilic substitution reaction. That means whenever the elimination is taking place through the SE1 mechanism, there can be a substitution nucleophilic one molecule, that is a SN1 reaction also may takes place. So, there is always a parallel reaction to this E1 mechanism, there is a SN1 mechanism also. Always 100% E1 you never expect, always a small quantity goes into the SN1. Similarly, in the SN1 you may expect a E1. We have a separate discussion when SN1, when E1 takes place, under what condition, which becomes major, which becomes minor, we will discuss later. But there is an always chance, because both SN1 and E1 have a common intermediate, that is the carbocation. So, from this if the elimination, that is H is dropped, you will get an alkene. Instead, if the OH attacks there on the carbocation, you will get an alcohol, that is a substitution reaction. So, finally, the mechanism is passing through the 2 steps. Step 1, ion formation, that is ionization. Step 2, OH minus taking the proton and getting the double bond, this is called step 2. So, there are 2 steps are there. Out of these 2 steps, step 1 happens to be the slow step. In the slow step is that, therefore, we decide it is the rate determining or RD step it is called. So, in this rate determining step, what OH is doing means simply waiting to get the carbocation. OH is attacking in the second step, which is a very fast step. So, therefore, in the slow step, only alkyl halide becoming into carbocation. Therefore, rate depends on only alkyl halide concentration, but not on the concentration of the OH minus. Therefore, we can claim that or state that, so the E1 mechanism is independent of the nucleophile or OH minus concentration. Only the alkyl halide is the rate determining molecule. So, therefore, it is called E1. 1 stands for the unimolecular elimination reaction, passes through the carbocation. Therefore, the solvents, if it is polar solvents, carbocation formation, intermediate is stabilized by the polar agents, so the reaction is more facility. And similarly, whenever a compound has a rearrangement taking place, means always you can expect it is a even type of the mechanism. So it passes through carbocation, means generally carbocation, if it is a 2 degree form, it will become 3 degree, or even in the 3 degree also there may be a stabilization of side by carbocation by some other mesomeric effect or other phenomena. Then the migration of carbocation, ring expansion, all such type of the complicated issues will come whenever carbocation is coming. So therefore, even mechanism is going through 2 steps, and in the even mechanism the concentration of the alkyl halide alone will decide. That's why it is called a even, that is our unimolecular elimination. So let us take the another mechanism, that is E1CB. E1CB. Any molecule from HCl, for example, from HCl if you remove the H plus, the Cl minus is called conjugate base of the HCl. From water you remove H plus, you will get OH minus. OH minus is called conjugate base of the water. Like that, from ethyl chloride, if you remove the H plus, what you get is called conjugate base of ethyl chloride. So here in the conjugate base of the ethyl chloride will be the rate determining step. How the reaction takes place here, you see. So this is the ethyl chloride, right? From the ethyl chloride, if the mechanism passes through, first H plus is deleted, let us say, then what comes is called carbanion of the ethyl chloride. So one H plus is less, otherwise it is ethyl chloride, isn't it? So this compound is known as what? A conjugate base of Cb of ethyl chloride, right? Cb of ethyl chloride. Now this one Cl, this minus will be coming here and the 2 electrons will be going, you get a double bond formation, Cl will be out and ethyl chloride is formed. So in this reaction also 2 steps are there, but it is found that the second step is the slow step. The reason I will explain. So second step is the slow one, this is fast one. So the rate of reaction will be the second step here. This step is involving the conjugate base concentration. If the more means more, less means less. So in the first step, the OH minus is coming and taking the proton, H plus is taken away. So anion is formed. Now let us have a comparison here. In the ethyl chloride, first Cl goes, you will get a carbocation. This is even mechanism. In the E2 mechanism, both simultaneously, H and Cl simultaneously goes, E2 mechanism. First Cl minus goes, carbocation comes, that is even mechanism. First H plus goes, a carbanion comes, that is even Cb mechanism. So no intermediate is involved, that is E2 mechanism. Carbocation is involved, that is even mechanism. Carbanion is involved, that is even Cb. Now when the carbocation, simple compounds undergo E2 mechanism. When a tertiary type of alkyl halides are involved, then a E1 mechanism. When E1 Cb taking place, what is the intermediate? I said carbanion. Under what conditions carbanions are stabilized? Carbocations are stabilized when electron donating groups are there. So when carbanion is stabilized means here you must have a group which can stabilize the carbanion. That is the main important point here. A group I must have attached to the carbanion which can stabilize the carbon. Under what conditions means the best group which stabilizes the carbanion is first directly the fluorine. When fluorine is attached, it will withdraw the electrons, stabilizes the anion. Another best group is CF3, that is the fluorines are not directly through the carbon they are attached. This also shows a strong minus I, this shows minus I effect. This shows minus I as well as minus hyperconjugation also. Whenever CF3 is there, this shows minus hyperconjugation and stabilizes the carbanion. You too can have a benzene ring like phenyl group. The phenyl shows minus M effect and stabilizes the system. Phenyl can have a now then extension of the either of the fluorine or a CF3 or a nitro type of groups, strong minus M group attached with minus M. In such cases also the stabilization of the anion will be more. The point you must remember, there are 3 or 4 types of the classifying these 3 reactions. One is both simultaneously going, Cl going, H going, which going out based on that we can remember, or the rate determining step. In the rate determining step here, it is the only the alkyl halide alone deciding, conjugate base of the alkyl halide is deciding rate. Alkyl halide as well as the base both are deciding, that's why E2, E1, E1 with Cb. What intermediate comes? Carbocation coming E1, carbanion coming E1 Cb. No intermediate, both come going simultaneously, it is the U2 mechanism. So, simple ethyl chloride type of compounds undergo this. Groups stabilizes the carbanion will undergo first H plus goes out and the carbanion is formed. Groups which have got stabilizing the carbocation, first Cl will go and then the carbocation is stabilized and goes. So, all these 3 types of reactions are taking place, but in general even eliminations will be always dominating in general as a whole. Compound, if it is simple, no doubt E2 eliminations will be taking place. When a taken compound core structure, if it is changed, core structure means skeleton structure of the compound, if it is changed in the final answer, then definitely we can go for the expectation of a through carbocation, that is a rearrangement takes place through the carbocation. Carbanions generally will not undergo rearrangement, carbocations will take one example for that rearrangement involving elimination. In an elimination, one example here, a tertiary butyl attached to a system of a compound like this. It's actually a neopentyl with neohexane type of core structure is there. This compound when treated with the alcoholic KOH. Now the Cl is the one which is going out, there is no dispute that Cl goes out. But which hydrogen goes out means it is not the same hydrogen as per the elimination principles here. The chlorine containing attached next carbon, if hydrogens are there, this hydrogen will be eliminated. So, H and Cl. This side there is no hydrogen. So, therefore, the compound what we expect, only the one answer, that is this type of the compound is expected. But unfortunately, this will be the only the minor product. Major product will be some other product is formed in which the compound is becoming into this type of compound. This is happen to be a major product. How this compound is formed, and this neo type of structure has been changed into the iso type. How it is formed means, now the mechanism shows like this. If it is simultaneously eliminated, E2 mechanism, then this must be the reaction. But sometimes if E1 is allowed, first Cl minus is going out, and then what you will get, a carbocation is formed, which is a 2 degree carbocation right now. But if this CH3 group with 2 electrons, if it is shifted to this carbocation, the step I claim as a rearrangement step. In this rearrangement, what is the achievement means, 2 degree is going to become into the 3 degree. So, we have a rearranged carbocation. So, let us say this is intermediate 1, I1, let us say intermediate 1, through rearrangement converted into intermediate 2. This is also carbocation intermediate, but which is a 3 degree carbocation, which has got now the 3 inductive effect, 3 plus 3 plus 1, that is 7 hyperconjugations here, only 3 hyperconjugations and 2 inductive effects are there. So, either way the 3 degree is more stable. So, therefore, the CH3 minus is shifted from this carbon to this, there is a 1-2 shift only, CH3 with 2 electron, therefore, CH3 minus is shifted in order to change the 2 degree into 3 degree. Now we have an option of eliminating the hydrogen either from the left side or from the right side. So therefore, there may be another product also may be formed like this. This also may be formed because if the hydrogen is detached from this side, left side, you will get another product also. But mostly obeying to the Sedgwick rule. Sedgwick rule says whenever there is a 2 beta hydrogens, the hydrogen, that is the carbon with less hydrogen, carbon will undergo elimination. So this H is removed and the double bond. And if you count the hyperconjugations also, this will have 3 plus 3 plus 3 plus 3, 12 hyperconjugations are there. Here only 3 plus 1, 4 hyperconjugations are there. So this will have the more stability. So therefore, this carbocation losing this hydrogen and giving this type of the major product. If this hydrogen is detached, you may get that one also. Another minor product is also formed. But a simple direct question now, if this compound treated with alcoholic KOH, is it a E1 or E2? Which is the possible mechanism? Straight away question. So without writing all the detailed mechanism and all that, one cannot decide. But we have a chance here. See the core structure here. Core structure is neotype. This is not neotype. That the core structure has changed. How the core structure changes means through rearrangement. When rearrangement comes through a carbocation, not through carbanion. So carbocation means it is a E1 mechanism. So therefore, answer goes to the E1, not to the E2, right? So if it is a like this, for which also E1 or E2 you can propose, but there is no betterment in the intermediate stabilization and all that. So therefore, it will be E1 mechanism is the right answer for the answer. If it is given like this, it should be the E1 because rearrangement we are claiming. So the topic substitution versus elimination is we are taking alkyl halide and the base is common KOH. Therefore, to decide whether it is substitution or elimination, certain factors we have to consider. One is the type of alkyl halide. If the type of alkyl halide is 1 degree, substitution is preferable. If it is a 3 degree alkyl halide, it is elimination. An example, if it is N-butyl chloride, mainly undergoes 1 degree. If it is tertiary butyl chloride, elimination is the preferable one. Both are alkyl halides. If the reagent is common, nature of the alkyl halide is some extent will decide. Another factor is a type of a base. What type of base I am using, nucleophile I am using. That is a stronger the base, elimination. Stronger base I am using, elimination, and the weaker base substitution is taking place. Weaker base example is here aqueous KOH. That is KOH dissolved in the water, it is called aqueous KOH. Alcoholic KOH here. Alcoholic KOH means KOH plus ethyl alcohol. Any alcohol you can take, but normal alcohol is a potassium hydroxide and normal alcohol, ethyl alcohol, you mix it. This is called alcoholic KOH. So these two factors are influencing. The stronger the base, elimination, because in the elimination HCl is going out. HCl is an acid. To take out this acid, I must use a stronger base. Alcohol dissolved KOH is a stronger base. Water dissolved KOH is a weaker. As the water you become more and more, the KOH concentration is decreasing, therefore it will become a weaker the base. So the one is the type of alkyl halide, the another one is the type of the base. Both are influencing the reaction. Here is an example that I want to prepare a ethyl and a tertiary butyl containing a ether. I want to prepare a ether, ethyl tertiary butyl containing ether, which can be prepared from the take ethyl chloride and treat it with the sodium salt of tertiary butyl alcohol. if this minus attacks, and then the Cl will go and you will get a substitution reaction. This is called a substitution reaction, nucleophilic substitution reaction. Specifically it is substitution, under that specifically nucleophilic substitution leads to give. Instead, if this works as a base, the ethylene may undergo elimination also. Then the product will be slightly different, that is ethylene. Ethylene also may be formed if this works as a base, because sodium salts of alcohols are bases, then a side product may get ethylene also. The same ether can also be prepared from the tertiary butyl chloride. Tertiary butyl chloride is the compound on which a sodium salt of alcohol ethoxide may be taken. This ethoxide may attack and replace the Cl. You may get once again the same substitution reaction. You will get this one, nucleophilic substitution reaction. Or if this works as a base, the compound may undergo elimination and you may get a, like this alkene may be also be formed. So elimination giving this alkene. So this is a side product, this is an elimination reaction. Now to get this particular compound, that is ether, I want to prepare a ether. Both are nothing but the application of Williamson synthesis, alkyl halides with alkoxides giving the ether. Alkyl halide and alkoxide giving the ether. Now it depends on the type of the alkyl halide. This is a 3-degree one. 3-degree one always prefers a elimination reaction rather than substitution reaction. So therefore, when the scheme 1, this is the first scheme, let us say this is second scheme. Now the question is, to prepare this ether, is the scheme 1 is better or scheme 2 is better, means in the scheme 2 I have chosen a tertiary alkyl halide as per the previous chart. Tertiary one would like to become elimination. Why means in the elimination you see 6 hyperconjugations are there. 6 hyperconjugations. According to the Sergeff rule also, it is 2 alkylated or the more substituted alkene. So 6 hyperconjugable hydrogens means this is more stable. More stable means then this no hyperconjugable the alkene. So this is no alkyl groups are there. So this is less stable and more stable. Always to get this one, there are 2 different types of the side products. If the side product this is more stable, more will be the alkene side will be going, less will be the. Therefore, always better take a 1-degree alkyl halide. See that I want a substitution product, therefore 1-degree alkyl halides prefers a substitution. Tertiary alkyl halides goes a elimination. So therefore, this will be the good method and this will be the bad method. So it depends on the nature of the alkyl halide is the first governing factor. So based on the alkyl halide nature, 1 degree prefers a substitution, therefore scheme 1 will be the better one. Okay. There is a special case of substitution in the aromatic one. If a chlorine is there on the benzene, when I add a concentrated NaOH, right, and then we have a pressure and temperature, then the reaction taking place, we are getting a phenol, and this happens to be absolutely a nucleophilic substitution reaction. But the same compound, if it is treated with the sodamide NaNH2, we expect the same type of the nucleophilic substitution reaction taking place, and you will get an amino type of the compound, right? This also we take it grant as a nucleophilic substitution. In the aromatic plane, with reference to this plane, the one side OH will be coming and slowly taking place. It is happens to be a nucleophilic SN2 type of mechanism. Substitution nucleophilic bimolecular reaction is taking place. Therefore, we go for this type of the explanation side by this is coming slowly, that is going and the reaction is forward. But in this reaction, the mechanism has got some doubts. With reference to only the chlorine, there is no point. But if there is a methyl group is there as a reference group, if there is a methyl is there, there is a chlorine is there, Then this compound, when I treat it with the sodamide, what is the expected answer as per this SN2 means the chlorine will go, NH2 will come. This is what your expected answer. But it so happened that this becomes only a minor product. Major product is some other product which is unexpected product, that is meta amino product has come. Where from this meta product is coming and why it is major also? There are two questions are coming. How this product is formed, meta, chlorine is at para, and how the group comes at meta. This is the first question. Another question is, if at all that is also formed, okay, some mechanism, why it has become major also? Unexpected product has become major now. So the mechanism is said like this here. Why this is major means we are explaining offering a mechanism. The mechanism is said to be a sign substitution or benzene mechanism or elimination addition mechanism. The mechanism simply also you can say elimination addition mechanism. What is this reaction means? In this compound, first H and Cl is being eliminated because of this sodamide. Sodamide is a stronger base, right? This is a strong base. So therefore HCl is being dropped out. When HCl goes out, there comes one more, already a bond is there, one more bond is formed. This compound, a benzene containing a triple bond, is known as benzene. However, in the benzene what we get, we have an additional group methyl. So let us call it a methyl containing benzene. But the benzene triple bond is at a specific place, not wherever I want. So at this particular place this one is there. So what is detached is minus of HCl, right? This HCl will react with sodamide. HCl will react with the NaNH2 what I added. So this forms into sodium chloride and the ammonia. Now this ammonia will dissociate into H plus and the NH2 minus. Now this two pieces will add on this triple bond. Now which will be added to which side is the question. If the NH2 adds on the para, H adds on the meta, you will get this type of. If NH2 goes to the meta and H adds here, you will get this type. So therefore two types of the answer, that is a para answer as well as the meta answer, two are coming. Now the second, how the meta is coming, I explained, because of the NH2 has a chance of attacking either at meta or at para, therefore meta is coming. That is the why meta comes. Now why only meta comes major means, now the methyl group we have seen that methyl is a plus hyperconjugation and plus inductive effect showing group. So therefore the incoming group with reference to the electrophilic substitution, the toluene, whenever the CH3 is there, at ortho, at para, because of these two effects, negative charge will be increased, negative charge increased. That's why whenever you do the electrophilic substitution, it goes to the ortho and the para. So the methyl group is known to direct incoming group electrophile to the ortho and para. Are you now getting a electrophile here? No, it is a minus group coming. So therefore let us reframe the statement. Original statement is methyl group directs the incoming electrophile to ortho para. Now I say the same thing, methyl group direct the incoming nucleophile to the meta, not to the ortho para, to the meta. That's why meta product. That means at ortho, para, ortho, negative charges are there. So I am applying a negative, negative cannot attach at negative. So it goes to the where electron density is less. That's why meta is becoming the major. So similarly, you too can have another questions like this. If the chlorine is at para, you are getting para and meta, right? If the chlorine is at ortho, with reference to the methyl, what are the answers means? What intermediate comes, let us see. The intermediate will be like this, right? In the elimination reaction, intermediate comes. So therefore now the products will be NH2 can go to the ortho or meta. Once again meta will be the major one. So NH2 can go to the ortho plus meta. of which again this will be the major one, meta will be the major one. Once again the chlorine can be at meta, then what happens? This question also can be asked. Then what are the intermediate? Means one intermediate is the triple bond may formed at removing the ortho hydrogen. This is one intermediate. Another intermediate also may be formed. Triple bond may come here. Both intermediate we have already discussed. If this intermediate is nothing but the same one, so therefore para and meta comes here. From here para and meta, meta will be the major one. From here ortho and meta, again meta will be the major one. So finally the answer will be the ortho plus para plus meta. In both the cases major, so therefore meta will be the major one, double major will be there, these two will be the small product will be there, and meta will be the major. So therefore the metachlorotoluene will give the ortho amino product, orthotoluidine we say, orthotoluidine, paratoluidine, metatoluidine, all the three answers will come, of which meta will be the huge amount of the meta product will be the major product will be formed. All this we are explaining through an intermediate called benzene. It is highly reactive, and in which the bonding is also has got some ambiguity here. It is not the 2 pi bonds. In fact, 1 sigma, 1 pi is everybody knows. The third one is formed. How this benzene third bond is formed means one vacant orbital, one sp2 hybridized, one is a Cl goes out, let us say. So there is a vacant orbital, there is a filled orbital, a sidewise overlapping of the both are sp2 hybridized, sp2 hybridized vacant, sp2 hybridized filled orbital, both will have a sidewise overlapping hybridized, therefore it is a sigma bond. So this is a sigma bond sidewise overlapping, highly reactive, which undergoes an addition reaction and open up and add this type of the products. And however this type of the reactions are now and then coming in the IIT examination also, so the answers will be like this. The other properties like reduction of alkyl halides, that is alkyl halides when they are reduced with a simple reagent like tin HCl or lithium aluminum hydride, that is vigorous reducing agents, they can be reduced with to give the alkanes are formed. In fact, this reaction we have observed in the preparation of alkanes. Similarly, Wood's reaction is also one of the popular reaction. In the Wood's reaction, the alkyl halides are treated with the sodium metal, metallic sodium, in presence of a dry ether. Dry stands for the no water, anhydrous condition of ether. If it is, it's only a solvent. However, it breaks, the NaX is formed, R will be doubled, and two R's are joined, you will get RR, provided if you take 2 sodium, 2 NaX is formed. The drawbacks or the advantages of the Wood's reaction are better discussed in the alkane topic, and this is no doubt is an excellent reaction. It has got a lot of scope to ask the questions and all that, but fortunately we have covered this in the alkyl halides, so therefore the Wood's reaction is already covered in the alkanes. The other reaction like Grignard reagent formation, Grignard reagent formation. The alkyl halides when treated with the magnesium metal, this also metallic magnesium is taken and treated in presence of the dry ether. The reaction condition is very much similar, metal is added and dry ether is maintained. Now a sort of that type of reaction also follows, but under different conditions the reaction was studied, and the magnesium reacts with Rx and forms into RMGX, wherein the alkyl group is directly attached to the organic compound, that is metal. Organic and metal is called organometallic compound. This reagent is specially called a Grignard reagent. The Grignard won a Nobel Prize for the introduction of this type of the reagent. The reagent is so versatile and it has got a multi-dimensional applications. One of the simple application is when you add water, the water hydrogen comes with R and alkanes are produced. Variety of alkanes, using the heavy water you can prepare a Ds containing alkanes, and a huge number of the applications like Grignard reagent reacts readily with the carbonyl compounds, undergoes nucleophilic addition with the acids, acid derivatives, and huge number of reactions with the carbon dioxide, H cyanides, and so on we have. So the Grignard reagent, the applications will take in separately, but how easily the Grignard reagent can be prepared here can be understood. So magnesium will take away the one halogen, that is, it is a byproduct is just the magnesium is inserted. In fact, no byproduct is formed. The magnesium inserts and you will get RMGX formation. This is what the another reaction.